we've seen that the L plus or minus operator doesn't do very much to the total angular momentum. What about the z component of the angular momentum? So let's try that next. Okay, so let's ask, what about Lz? If we apply the Lz operator then to our new state that we get from applying L plus or minus to our y lambda m, right? What do we get now? Again, will we get a pure state back again? Will this give me back some constant times then the original state I'm starting with, L plus or minus y lambda m? Will I get a pure state of Lz? And if so, what value of the pure state will I get? Now, this analysis is going to parallel very closely to what we had just done. So once again, we will write out our operators applying to our state. And for the same reasons as before, we would love to have these commuted so we can pay the cost of the commutator and then get our operators in our preferred sequence, Lz acting on y lambda m. In this case, y lambda m we know is also simultaneously pure with respect to Lz. Its pure state value, though, is now given by the m index, which we know is some integer, and the angular momentum Lz will be some integer times h bar. And because it's a pure state, that then is just multiplying my y lambda m again. As before, my constants m h bar can be factored out. So what I end up with then is, at least for the second term, once again, a term in the form that I'm hoping for. I'll get a plus. This constant here has come out. That will be m h bar. Then it's been pulled out of the L plus or minus, so the L plus or minus is still acting. And what it's acting on is the y lambda m. So indeed, what I am getting back again is a constant. Let's make sure it's clear what the constant is. It's m times h bar. Times my original state. So this first piece, at least, seems to have worked out quite well. What we, again, need to determine now is what is this commutator and what are its effects. So let's take a look at that commutator. So let's note, if we were to calculate it, if we now do the commutator of Lz with L plus minus, we recall the definition of L plus minus, of course, right? That was, we had written that up just a little bit above here. Here you go. It's again got the Lx and the Ly with the plus or minus. So it'll be Lx plus or minus I times Ly. And this is the beauty now of having computed all of our possible commutators, our Lie algebra, because we know these individual, the values of these individual commutators. So I'm going to have Lz commuted with Lx, then plus or minus I times the commutator of Lz with Ly. And if we take a look at our table of results, we want Lz with respect to Lx. Now, where was that here? Here he was. Lz with respect to Lx. And I'd like you to notice I've corrected a typo that I made in the original video. When I was going in my cyclic permutations, x goes to y goes to z. Z then goes to x, and then I had an error because x then, of course, goes to y. So the commutator I'm looking for is Lz with Lx. That's I h bar Ly. So Lz with Lx is I h bar Ly. And then I have plus or minus I times. And the commutator of Lz with Ly, I should find that up here. I almost do, but I have this in the backwards order. Right? So Lz with Ly will be the opposite of this. It will be minus I h bar Lx. So there's an actual minus sign I h bar Lx. And this is then something I think we can arrange into a more suggestive form for ourselves. If we look at, for instance, the upper sign here, right, we'll have I times minus I. That's just a plus 1. Right? So this, I'll just put it this way. This I times this minus I gives me a plus 1, and then h bar Lx. So it comes with a h bar Lx, but there's this plus or minus sign. So I'm going to have plus or minus h bar, And my first term, as we just said, would be Lx. So that takes care of these terms. This term I want to reproduce. I've already factored out the h bar. I need to put in an Ly and an I. And now I just have to be very careful with my signs. In the upper choice of sign, it was a plus term here and a plus term here. So with the upper choice of sign, a plus term here would require a plus term there. For the lower choice of signs, I would have had a minus h bar pulled out, but this term has to come in as a plus I h bar Ly under either circumstance. So this minus had better be hitting a minus I Ly. So I end up with a net minus h minus I Ly, which would be plus I h bar Ly. This term then exactly reproduces the original term. And the really cute thing about this, as I think you can see, is that when I look at what that commutator has just given me back, it's just giving me back plus or minus h bar, and this term is nothing other than the original L plus minus operator that I started with. So let's put a little bubble around that. That's a little side discussion. And I want to put a box around this one. This is a very important commutator. Now, applying my commutator, then what goes here is going to be simply plus or minus h bar times L plus or minus. That's the value of the commutator, and that commutator is then applied to y lambda m. So now you see we are in terrific shape, because once again I just have my original state coming back again, and I now have two terms with my original state and some constants. So let's just gather all that down here together into a nice neat equation, a final result. So Lz applied to L plus or minus y lambda m will equal something times L plus or minus y lambda m. And that something is apparently mh bar plus or minus h bar. So factoring out the h bar, that was mh bar plus or minus 1 times h bar. So that is my result here. So there's an important lesson on this one then too. So L plus or minus on y lambda m also is pure, right, with respect to Lz, but with a new eigenvalue or new pure state value with new value, and the new value is now m plus or minus 1 h bar. The plus or minus depending upon whether I've applied L plus or L minus.